Okay, so good evening, everyone. I am Shomodi from Indian Institute of Science, and I'm taking these weekly sessions for the NPTEL course Advances in UHV Transmission and Distribution every Saturday from evening 6 p.m. to evening 8 p.m. And these sessions are mainly meant for clearing your doubts. If you have any confusions or doubts regarding the course which is being taken presently by Professor Subba Reddy of our department. So if you have any doubts or any confusions regarding this course, you can ask me in the live sessions. Some of the important topics which are being covered in the course, I have taken them up and I'll be discussing them in bit details. Like one of the topics was about numerical field computation, which I have been describing for the last 1 to 2 lectures. And I'll continue that. And I'll give a brief recap, quick recap of what I had discussed in the previous class, and then I'll be moving on to the new topics. So basically, we were looking into this charge simulation method, and in this charge simulation methods, we had seen on how we can find out this potential coefficient matrix P, and from that P, how we can find out the unknown simulation charges. Basically, charge simulation method is a domain boundary based method in which we discretize the boundary of the geometry into discrete charges. It can be point charges, line charges, or ring charges. I had described you of point charges, and choosing the simulation charges, the type of the simulation charges, it basically depends upon the geometry of the system. Basically, if you have an axisymmetric system, that is a system which is symmetric, a geometry which is symmetric about a particular axis, in that kind of system, we generally use ring charges, or we can, for a straight conductor geometry, we can use point charges also. So I had described you using point charges. So basically, we had a rod plane type of electrode, and we had discretized that into multiple point charges, as you can see here. These are the different point charges. According to the geometry of the system, we have discretized it into different contour points. And for each contour point, we had one simulation charge, right? So these are the simulation charges. So these are the different simulation charges which we had used. And based on this, we had formulated how we can find out the P matrix. I'll give a quick recap. So this was our P matrix basically for a point charge. And this P matrix is going to vary based on the type of charge you are using. So this is basically Pij, and it is a n cross n matrix. Suppose you have discretized the geometry into 10 or say 100 contour points, then basically we will have P as a 100 by 100 matrix. And the right hand side matrix, that is V, that is given by the boundary condition, that is the voltage which is known to us. Suppose we have a point plane electrode like this. We have this point electrode here, and say we have the ground electrode here. We are applying a 100 kV voltage. So on any point which is on this point plane electrode, basically we know the voltage of that point, and that is 100 kilovolts. So based on the boundary condition, which forms the right hand side matrix, this is the basically the RHS matrix. And we have developed P, so we can easily find out the unknown simulation charges. That is the value of this Q. So Q is basically a column matrix, and its size is n cross 1. So once you know Q, you can find the electric field or potential due to these point charges at any point in the domain. And we all know that here we are, since there is a ground plane, in order to eliminate the effect of the ground plane, we are using the of um, concept of image theory. In image theory, what we basically do is we, for every point charge above the ground. Yes, Anwar, you have any doubt?
Sir, actually, sorry to interrupt you in the middle of
Yes,
this
yes, that's
session.
fine.
Actually, the
Hmm.
thing is, sir, I got the notification only yesterday regarding this attending this session. So this will be my first session with you regarding this subject.
Oh,
So just to clarify a few points, will you
hmm.
be sharing us the notes after that, or
Basically,
is the
the
recording?
system here is I have been instructed by NPTEL to upload the recording as well as the notes in their portal. So basically, I have a Google Drive link and I'm uploading there. So I am of the opinion that they are directly sharing it to you. Uh, is it some other participants? They can confirm. What is the system? Those who have attended these sessions, are you getting the recordings of the notes of these sessions? Mr. Raju, anyone can tell or
Yeah,
Purushottam?
it is there. It is available.
Okay.
Okay, fine, sir. They will be sharing it via email, I believe, right? The link.
If you have any problem, you can tell me. I have made a WhatsApp group actually. So there you can join. At the end of the
Correct.
class, I'll be telling you.
That's okay, sir. Yeah, thank you, sir. You may continue,
Okay.
sir.
Okay. Okay. So as I was telling this charge simulation method. So here we are finding, so once we have found out the unknown simulation charges, that is Q, we can find out the potential and field due to these unknown simulation charges at any point in the domain. And one more thing which I was emphasizing was the use of the image theory. So image theory is basically to maintain the equipotentiality of the ground plane. So for every point charge above the ground plane, we assume an equal and opposite charge beneath the ground plane, and then we remove this ground plane. So the effect of the ground plane is included as an equal and opposite negative charge beneath the ground. And our computation using this charge simulation method is valid only. Suppose if you take it as x equal to 0 plane, this one is suppose ground is at x equal to 0. So my computation is valid only for x greater than 0. That is the above portion. Only here my computation. So if you want the field at this point, you cannot find it out using this simulation charges, this charge simulation method. So the formulation there will be entirely different. You have to take equivalent charges and then you have to do it for beneath the ground. So this calculation is for everything above the ground. Okay. So here I have described the formulation, how to find out. So basically we are trying to find out the voltage at the known points. Suppose I have the contour points like this. So these are my contour points. And these are my say 11 charges and 11 image charges are there. So the potential at any point, say at point P, will be due to all of these charges, right? So basically this is a point charge and we know what is the expression for the electric potential of a point charge. It is basically 1 by 4 pi epsilon naught Q by R, right? So basically we are trying to find out using this the basic theory for point charges, we are trying to find out the potential using superposition theorem. And we know what is the potential at P, right? That is the applied potential. So like this, we can find out the potentials for all the different contour points. And basically, we will form a column matrix of V, which will be like this. So this will be V1, V2, dot, 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 up to Vn. Then we will have this potential. This is the potential coefficient matrix, total thing. So we will have n cross n here. So it will be P11, P12, P13 like this it will be. So we will have this. Then we will have the Q1 dot dot Qn. So basically we can find out Q is equal to inverse of P multiplied by matrix. So from this we can find out the simulation charges Q which are unknown, which is unknown here. So using this Q, we can find out the electric field and potential at any point within the domain. For basically, we are using this charge simulation method for field computation, right? For numerical field computation. So this is the basic theory behind this charge simulation method. So then we had moved to a different topic, which one of the students had raised in the class. It was about the mechanical oscillations or vibrations. So these mechanical oscillations or vibrations due to minimize this effect of electromagnetic interference and electromagnetic compatibility, we have a minimum clearance distance between the different high voltage equipments and transmission lines and all. which is known as the right of way. And we should, apart from this right of way, we should also make sure that all the EHV lines, the extra high voltage and ultra high voltage lines, are mechanically tight. So in order to maintain that and make sure that all lines, all transmission lines are tight and taut, we need to understand the different kind of vibrations, the different kind of oscillations occurring in the system, right? So basically we have three kinds of vibrations: the alien vibration, then we have the galloping vibrations, and then we have the wake induced oscillations or vibrations. So there are different kinds of, basically due to the pressure vortex, due to the flow of wind, there is a pressure difference, and that causes multiple moving up and down of these transmission lines. So there are three kinds of vibration: one which occurs in the normal condition, and galloping vibrations occur mainly in the extremely low temperature areas where there can be ice deposition in transmission lines. So you can go through these notes, and this one I had discussed in details. Wake induced oscillation. Then we, to minimize these oscillations, what we can do is we can install spacers of high mechanical and dielectric strength. Also, we are installing vibration dampers in the lines, which can keep these EHV lines mechanically tight. So then we had moved to what is called as audible noise, right? So audible noise, basically, we have heard of, every one of us had heard of the term corona discharge, right? So this corona discharge basically occurs due to the local breakdown of a air column, right? So when these high voltage lines, extra high voltage or ultra high voltage lines are passing through some area, and in the local and in the local surrounding of the transmission line, we have a very high electric field, and this electric field often exceeds the breakdown strength of air, which is 30 kV per centimeter. So once this breaks down, there is a local discharge in the air due to its breakdown, and we hear a hissing sound, which is produced due to the movement of the electrons in the air column. And this type of sound, this is one of the sources of audible noise. Also, we have the humming sound in the transformers. So these are the different sources of the audible noise. And we have the different, according to the set standards and the criteria. It was laid down by a scientist named Perry. So he has listed down the different ranges, the ranges of audible noise. One which is the acceptable range is less than 52.5 decibels, and anything above 52.5 till 59 dB is still allowable. But most complaints are raised when the sound is greater than 59 decibels. And how do we measure this audible noise? Audible noise is represented by the sound pressure level, or the SPL. So SPL is basically the length of the air column multiplied by the pressure of the air column. And we have a equation for audible noise in terms of the SPL, which is given by 10 log SPL by 20 into 10 to the power minus 6 decibels. So basically, I'll be doing 2 or 3 numericals based on this audible noise, and each one of you can try it. Any confusions from the previous class or any doubts pertaining to the course? Anyone? Any doubts? Anyone wants to clarify?
Sir, good evening, sir.
Yes, yes. Good evening.
Sir, actually, in last week, I have requested you to give some guidance for examinations, sir.
Examination, what type of guidance you want? Basically, whatever is covered in the course, we'll have some mostly MCQ questions, I think, in the exam.
Sir.
If you can particularly specify what type of this guidance you want, I can help you out.
Sir, that means how many questions we will get, and that's actually you told that section is seeing by another person.
Yes. That is being seen by another person. So he was not available in the previous week in our lab, so I could not talk to him. So when is the exam actually?
24th September, sir.
Okay, still time is there. I'll next class I will get back. Okay.
Thank you, sir. Thank you.
Anyone else? Any doubts? Anything? Any questions?
You can go ahead, please.
Okay. Anwar, you are attending for the first time. So if you have any questions, you can stop me in between, right?
Certainly, sir. I will do.
So basically we were talking about audible noise, right? So audible noise, as I had described, this audible noise is related to the SPL level, right? Which is known as the sound pressure level. So it is basically given by this is a this empirical type of formula, and we don't have a derivation for this. This is based on experimental results and everything. So this just you have to keep this thing in mind. So first question I will do. The first question is, every one of you can note down or whatever is convenient for you to answer the question, you can do that. So the audible noise of a three-phase transmission line is 50 dB. Compute number one. You can keep one calculator in hand to solve the question. So you have to do the audible noise is given as 50 dB. First, you have to compute the SPL level. And it is also told that if a second source of 48 dB contributes at the same location, calculate combined dB. So first you need to get a clear idea of the different units, right? So what is the unit of audible noise and what is the unit of SPL? So unit of SPL is pascals and unit of audible noise is decibels. Okay. So can someone compute? Can you do this calculation? Anyone? I'll give 5 minutes. Just try. Otherwise, I will do it. Everyone should try it. Otherwise, there is no point in doing it. Anyone who has completed can raise the hand. I am waiting. Anyone who has done, please. If you have done the first part, you can tell. Or the second part, any part, if you have completed, you can tell.
Is it 2 Pascal, sir?
Yeah, correct. First question, first answer is 2 pascals. So basically, and you can try the second part also. Anyone, anyone else done the first part? Anyone? So if you want to compute, audible noise is given as 50 dB, right? So it is basically 10 log of SPL by 20 into 10 to the power minus 6. So this type of questions can come in the exam also. You can start practicing. 5 will be. So anyone else? Is it clear the first part? Any doubts? Anyone? Anushri, are you getting?
Yes, sir. Yes, sir.
Okay. Did you do the second part?
Yes, sir. It is at 127.78.
The total audible noise you are telling 127.78.
Yes.
How did you get? Can you tell? Anyone else who got the same answer?
So
How
that
did
given
you?
formula.
Yes. Yes.
So the formula is 10 log 10 SPL
Hmm.
upon 20 into 10 raised to minus 6.
Yes. So what is the second question? Did you understand what the second question is trying to tell? So it is basically telling that you have this 50 dB source and the second source also comes, which is 48 dBs audible noise in the same location. So what is the combined audible noise in decibels? So you have to find that out. So how did you do it? Can you tell? How did you get 127 dB? Because I have a different answer. How did you get 127? Can you tell everyone?
Sir, I have put SPL 50 and in this formula and addition between 50 and 48 by this
So,
formula 10 log 10.
so SPL is in pascals, right? SPL is not in dB. So
Okay.
this 50 dB and 48 dB, whatever is given, so that is basically in dB. You cannot put that in SPL because that's why I told first the units you have to check. So unit of SPL is pascals and unit of audible noise is in dB. And suppose if you have two sources, one source of 50 dB, another source of 48 dB. So the total audible noise you cannot add directly. So what you have to do is you have to find out for both the sources, you have to find out the equivalent SPL in Pascal. Then you have to add them. So that will be the combined audible noise in Pascal. So then you have to convert that SPL in Pascal to SPL in dB using this formula again. Anyone else did the second part of the question? So can you find out corresponding to 48 dB, what is the SPL level? If you can find that out, then it is almost done. The combined SPL, the total SPL level corresponding to 48 dB. So it is basically 48 will be given by
Anti-log of 4.8.
yes. So it is basically SPL. It is 10 to the power 4.8. It will be
63095.
No, it is 1.26 pascals.
No, sir. The anti-log of 4.8. Yeah, right. Right.
Okay.
1.8.
Okay. So SPL for this corresponding to 48 dB is, I'm representing by SPL2, and that is 1.26 pascals, right? So what will be the total SPL? The total SPL will be corresponding to 50 dB, it is 2 pascals, and
2.26.
corresponding to, yeah, so it is 3.26 pascals. So now you can find out what is the total audible noise in dB. It will be 10 log 3.26 by 20 into 10 to the power minus 6. So it will be over 3.26. Right. So it is coming around 52.12 dBs. Is it clear, everyone?
It's clear, sir.
Others, Mr. Purushottam, Mr. Raju, is it clear?
Clear, sir.
Okay. Anyone, any confusion, you can raise your hand. So try to solve it with me, otherwise it will be very difficult. So this was the first question. Second question. So second question will be similar. Everyone has to get the answer, right? So it is telling a three-phase line yields audible noise levels from individual phases. Okay, one more before going to this. I want to tell one more shortcut. So the thing is, suppose you have n audible noise sources, right? So you have n number of audible noise sources of AN1, AN2, dot, dot, dot. So I'm telling. So you have I number of audible noise sources. So what will be the total audible noise? So basically we have a generalized expression for this. So you can derive this easily. I'm just giving you total audible noise will be given by 10 log 10 summation of 0.1 AN. So this is the generalized expression. You can derive this easily. You have to find the SPL level for all the audible noise sources, add them up, and then again find the total audible noise. So this is the generalized expression. If you have I number of audible noise sources, it will be 10 log 10 summation of 0.1 ANI. Okay. So now this question will be much easier to solve. A three-phase line yields audible noise levels individual phases to be 55, 52, and 48 dB. Find the resulting total audible noise level. So anyone can try this question. So what is it telling? Basically, you have a three-phase transmission line, and each of the phases of the transmission line is yielding an audible noise level of 55 dB, 52 dB, and 48 dB. So you have to find the resulting total audible noise level. So everyone can give it a try. You have to basically use this equation. 10 log 10 of 0.1 ANI, summation of 0.1 ANI. Mr. Purushottam?
Hello, sir.
Yes, can you try this question?
Sir, I am trying, sir. 10 log 10, 55 plus 52 plus 48.
Check the formula once again. It is 10 log 10 of
10 log 10 of, sorry,
One
sir,
second,
0.
one second.
Into 0.1.
It is 11.9,
10 to
sir.
the power 0.1 taken.
11.9. So is the answer 11.9?
It is. Can you, the formula I had written it incorrect. Can you check once again? It is 10 log summation of 10 to the power 0.1 ANI. Yes. Anyone got the answer? So, Mr. Purushottam, can you tell me what will be the, if I apply the total audible noise equation, what will be the equation like?
Sir, 10 log 10,
Hmm.
10 to the
10
power,
log 10.
10 to the power, sir, 10 to the power of 0.1 into 150.
Yeah, 0.1 into.
155.
Where did you get 155? It is 55, 52, and 48. So it will be basically 10 to the
Summation of
power.
all.
It is like this. Is it clear?
Clear, sir.
Your voice is not clear, Purushottam. Can you come back once again?
Sir, I'm getting very low signal, sir, at my place.
Okay. Is it clear for you?
Yes, sir, I'm following, sir.
How much it is coming, Anwar? Did you get the answer?
It is clear, sir.
Okay. So it is basically around 57.3 dBs. Okay. Okay. So these are the two numericals which we have done. So just remember this formula and you will be able to solve this type of questions. So regarding audible noise, there are two more terms which I need to specify. One is called as L50 level. So what do you mean by L50 level? So suppose we are doing our experiments, anything in these transmission lines or something, we are doing this experiment on measuring this audible noise, right, throughout the year. So then suppose every day we are taking some readings. So in an year, suppose we have total 1000 readings. So it is that level, L50 level of audible noise is that level which is crossed more than 50% of the readings, by more than 50% of the readings. So L50 level is suppose we are doing experiments on measuring the audible noise throughout the year. Then more than 50% of the readings will cross the L50 level. This is basically the L50 level. And we have another term which is known as L5 level. Similar to L50 level, it is more than 5% of the readings will cross. So we, after taking all the readings throughout the year, we will check which reading is crossing, is repeating most. That is, it is crossing more than 50% of the reading. Suppose we have 100 readings. Suppose take smaller values. Suppose we have 10 readings. We will check which reading is crossing more than 5 times. Which reading is appearing more than 5 times. So that will be my L50 level. And we'll see which reading is crossing more than 5% of the total readings. So that will be my L5 level. Is it clear? Is it clear, everyone?
So just if you can repeat once this last line,
Okay.
please.
Okay, fine. So basically in audible noise, where we define audible noise, we have certain terms which we need, which has been defined by the standards. So basically in an audible noise experiment, we will be doing it throughout the year, right? To get an average of the audible noise, what to get a trend of what is the audible noise of that particular region. So basically with reference to that, we have defined two levels of audible noise. First one is L50 level. So L50 level is basically once we get all the readings throughout the year, we will see which value of audible noise or which reading is crossing more than 50% of the readings. That is, suppose we have 10 readings and suppose we are saying that more than 50% times, that is more than 5 times, my audible noise is greater than say 8 dB. So my 8 dB is the L50 level. And L5 level is more than same thing, the reading which has crossed more than 5% of the total readings. That will be my L5 level. Is it clear?
Yes, sir, clear.
Everyone, is it clear? Fine. So the next
it's
thing
fine,
is, okay. So the next thing is which is called day-night equivalent noise level. So basically, we are doing these experiments both in the daytime as well as in the night time, right? So during night, mostly there will be no background noise. And due to this absence of the background noise, the audible noise which we are obtaining during the night time, that is increased by 10 times. Because in the morning time, which the audible noise which we record, that will contain the impurities from the background noise, the spurious noises will come. So to compensate for that during the night time, since the background noise is unavailable, we increase the audible noise level by 10 times to account for it. So we have a formula for this day-night equivalent noise level, that is to compensate for the nighttime increasing this 10 times. So this one I'll write it down, then I'll explain. So basically during night, due to absence of background noise, the audible noise during night is increased by 10 times. To account for it. So the equivalent day-night equivalent noise level that is given by LDN, that is given by I'll write the formula first, then I'll explain. It is a bigger equation you can note down. So this is our formula. And what is this AN? This is the audible noise during daytime. This is the audible noise during. Okay, 1 second. Okay, suppose we are getting this total audible noise as 0.1 AN. So my daylight D is my daytime hours. So D is my daytime hours. So this is basically for my day, and the remaining this one is for my night. So if the day is for say sunlight is there for 10 hours, the night duration will be 24 minus daylight hours, right? So this is my basically the formula. And suppose if we include the rainfall also during the daytime and during the night time, so we will have a different equation, which is given by, suppose we have PD % rainfall during day and PN % rainfall during night. So our total, this one will be 10 log 10, 1 by 24 into T into PD by 100. Just this term will come extra. In place of D, it will be D into PD by 100. 0.1 AN plus it is 24 minus D into PN by 100 multiplied by 10 to the power 0.1 into AN plus 10 in T. Is it clear? Any confusion, anything? Just have a look at these two equations. If you have any doubts, you want to understand, you can tell me. Any questions, anyone? Or is it clear? So this will be clear when we solve some numericals, right? So the first question regarding this, so it will be question number 3. The L50 level. So the question, please note down, everyone. The question, note down the question. The L50 level of the 3 phases of a transmission line are respectively 50 dB, 58 dB, and 52 dB. If there is 30% rain during daytime and 70% rain during night, calculate audible noise, equivalent audible noise level, assuming 15 hours of daylight. Can you solve this?
Let's try, sir.
Yes, yes. Everyone can try. Everyone should try. Otherwise, there is no point.
Sir, can you put me the earlier, sir, the equation?
Yes, sure. These are the two equations. If you consider the rainfall also, it is the last equation.
So this is 24 minus D into PR
Yes,
into 10 power 0.1.
yes, yes, yes.
One line is there, it's not divided by, no?
No, no, Pn by 100 is there. Only Pn by 100.
Okay, okay.
So in this equation, just tell me what you are taking as An. What is the An you are taking? That is the only catch here. Otherwise, it is very simple. Everything else you know. You know D, you know PT, you know Pn. So what is the An value you are taking in this equation? Anyone?
So that combination of 10 log
Yes.
10, right, sir?
Yes, 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 correct. Combination, you have to take total audible noise of all that. 58, 50, 58, and 52. So what is the total audible, combined audible noise you are getting? Anushri, can you tell what is the combined audible noise?
So the combined audible noise is 160.
160. How did you get 160?
Sir, combined values 50, 52 and 58.
Did you listen what I had told? How did I solve the previous problems? If you have 3 audible noise sources, what is the combined audible noise I told? You cannot simply add the dB values I had told.
Yes, sir.
Yep.
I'll solve, repeat, and tell you answer.
Okay, tell me what is the combined audible noise value? How will you proceed? You tell me first that one, then calculation easily you can do. How will you proceed? You tell me.
So this will be 59.49.
Yes, that is correct. Anushri, can you tell how will you proceed to find the combined audible noise?
Sir, it is come 59.49. 50
How did you
actually.
how did you get?
Sir, they 10 log 10 into SPL upon 20 into 10 raised to 6.
No, how did you get? You tell me. You are not telling it correctly. You are not listening. You solve it in a paper, the total audible noise, which formula you are using, and send it in the chat box. You are able to access. Otherwise, switch on your camera and show me. How
Sir,
did you solve?
the formula is 10 log 10 summation of 0.1 raised to 10 raised to 0.1 into 50 into 50 plus 10 raised to 0.1 into 58 and 10 plus 10 into 0.1 into 52.
Correct. Did you solve it like that? Did you get the answer?
Yes, sir, I get it.
Okay. Then find the equivalent audible noise level, the LDN. So total audible noise is basically 10 log 10 to the power 5. That is 0.1 into 50 plus 10 to the power 5.8, 10 to the power 5. So this is coming out to be 59.49 dBs. So now how will you find the equivalent audible noise taking into effect this rainfall and the daylight hours and night hours? How will you do that? Samir, you were late today. You had any issues? What is the value of LDN you are getting? Anyone? Just you have to substitute in that equation. This is our equation. So what is D here? Anushri, what is D and what is PD and PN? Can you tell? What is D and PD here? Anyone?
30 and 70%.
Yes, sir.
Yes, PD is the rainfall during the daytime, right? So it is 30%. PN is the rainfall during night time. So that is 70%. And what is D? What is D here?
So 15.
15.
15 hours, correct. So
Sir, I'm
just
getting the
substitute.
answer as 63.9.
Correct, 63.98 dB.
Yeah.
So just you substitute, you can get it. So it will be 10 log 10 is basically 1/24 into D is 15, PD is 30 by 100, 10 to the power 5.949 plus if daylight hours is 15, night will be 9 hours, right? So it is 9 into 10 to the power 0.1 into, so 10 should be added, right? So it is 69.49. If you simplify this, it's 63. So can you find this LDN, equivalent LDN in SPL? That is in pascals. Can you find it out? So everyone, you are getting this, right? So what is this equivalent LDN in pascals? Which equation we need to use? It is 63.98 equal to 10 log SPL by 2 into 10 to the power minus 5. So basically SPL will come out. How much you are getting, Anwar? So it is coming approximately 50 pascals, right? So is it clear to everyone? Any confusions, any doubts? If it is clear, please tell. Otherwise, I will repeat it. Any confusions, anything? Am I audible? Hello?
Yes, sir.
Is it clear, everyone? Please respond.
It's clear.
Everyone, Anwar, is it clear? Okay, so this was all about the audible noise part. Next, I'll be moving to another topic, which is called as radio interference voltage, right? In short, we call it RIV. So, any idea what is RIV? Anything you have gone through the course, right? So, what is, how does it come? How is it generated? Any idea?
So that the communication signals.
So it is basically an interference signal, right? So it is the phenomena of interference of this power signals with the communication signal. So first we will look into how the RIV is generated. Means why, how is it generated? Then we'll look into the measurement circuit for RIB. So basically, how does breakdown occur? Breakdown of any gaseous medium. How does corona discharge occur? So we say that whenever the electric field crosses the threshold breakdown strength of air, there is a spark vis. But what is the underlying physics behind it? If you look into the physics behind the breakdown of gaseous medium, it is basically suppose there are two electrodes. Just think of it as two electrodes. One electrode we are applying the voltage, the external excitation, and the other electrode is grounded. So basically the medium in between is an insulating medium and it is not conducting. That's why it is an insulator. So now suppose if we go on increasing the voltage, so electrons will be emitted from the surface of the electrode, right? So once the applied excitation crosses the work function of that metal electrode, basically electrons will be ejected from the surface of the electrode. That is the cathode. So once these electrons are ejected, these are called the initiating electrons. So these initiating electrons will collide with the neutral gaseous molecules. So this in between the two electrodes, there is multiple gaseous atoms, neutral molecules, metastable atoms. These are there. So these electrons start colliding with this as they move haphazardly. They collide with the neutral gas molecule, and due to this, due to these collisions, there will be multiple generation of multiple electrons. Due to these electrons, electron collision with the neutral atoms, we will have multiple electrons. So these multiple electrons will again collide with the neutral molecules, and based on the energy content of the electrons as well as the neutral gaseous molecules, these collisions can be elastic as well as
Plastic.
yes.
The collisions can be elastic as well as
Yes,
second thing.
collisions can be elastic as well as inelastic based on the energy content of the electron and the neutral gaseous molecules. So due to these multiple collisions, a stage is reached when there is an avalanche or a flood of electrons within the two medium. So once there is flood of electrons, so obviously that medium will be conducting. And that is when we call the breakdown or flashover of the insulating medium occurs. So this is the basic physics and of the breakdown of a gaseous insulation. However, this corona discharge or the partial discharges, these are localized breakdowns. That is, within a point inside the gaseous air gap, we have a breakdown. That is the local area. There will be an intensification of electric field, and this discharge will be confined to that local area only. With time, if the properties of the this insulator will deteriorate, this discharge will gradually propagate and will cover the entire electrode. This partial discharge or corona, these are localized electrical discharges, and over time, if the field is sufficient enough, it can cause flashover or breakdown of the insulation. So this is the basic understanding. So coming to RIB, so as I was telling, the collision between an electron and an air molecule generates an ion and a secondary electron. So these multiple electrons, as I was telling, these are known as secondary electrons. So a collision between an electron and a neutral air molecule will generate another ion, that is ionized particle, and a secondary electron. The distance between these electrons and the air molecule is very less because of the mean free path, and hence we get a very sharp pulse with less rise time. And there will be a delayed decay. Lower energy content of the secondary electron. So basically, during this collision, the distance between the electrons and the air molecules will be very less. Because of collisions and all, then this distance will be very less. So there will be a pulse generated, right? Due to this collision and generation of multiple electrons, there will be a pulse generated. So what will be the characteristic of that pulse? So if we think, so this pulse, the rise time, for a pulse, there will be a rise time and a fall time. So this rise time is basically decided by the distance between these electrons and the air molecule during the collision. And the falling part, that will be decided by the energy of the secondary electron which is generated. What is the energy content of that? And this pulse is called as radio interference voltage, that is RIV. So it will have a very fast rising and a slow decay pulse. Will fast rising and very slow decay. This will be a typical RIV pulse. So as I was telling, this rise time will depend on the distance between the electron and the air molecule, and the fall time or the tail time, that will depend on the energy content of the secondary electron. So this RIV pulse is basically made up of further two pulses, right? One is the rising pulse. And another is the falling pulse. And so if there are different equations for this RIV pulse. So basically, if we have a positive RIV pulse, that is given by the equation of positive RIV pulse. It is basically a constant K plus into IP e to the power minus alpha T minus e to the. These are basically tested from different experiments. We don't know how these equations have come. This is basically the double exponential wave, which is used for impulse functions also. So, and another we have which is known as the negative RIV pulse. So this equation is a bit different. It is a constant K minus into the maximum peak T to the power minus 3/2. So this is an empirical formula which has been defined for positive and negative RIV pulse. So the characteristics of this positive from these equations, you can identify that for a positive RIV, since these positive ions will be heavier and this will hit the neutral atoms, as they collide with the positive ions will collide with the neutral atoms, and due to the higher mass of these ions, the rise time and tail time will be generally higher. Because the tail time, you can think, right, it is due to the process of decay of energy of the secondary ion or electron, whatever you tell. And since for a positive ion, the mass will be higher, so more time it will take to for this decay, and hence the rise time and fall time both will be higher for a positive RIV. So
Excuse me.
I'll write the. Yes.
Can you read the negative RIV pulse equation?
It is basically I minus, it is given by K minus is a constant.
Not audible.
multiplied by t to the power minus my someone can respond.
Yeah, not audible. The moment you started reading, no.
Am I audible?
Now, yes.
Yeah, now you are audible. Yeah, now you are audible. Can you repeat?
Yes.
Repeat the equation, please.
Okay. This positive RIV pulse you could hear, right?
Yes.
Okay, fine. For the negative RIV pulse, it is basically an exponential wave, and it is I minus is given by K minus, which is a constant, multiplied by the peak current IP into t to the power of minus 3 by 2, multiplied by exponential of minus gamma by t minus delta t. So this gamma delta, these are all constants which will depend on the rise time and the fall time of the RIV pulse. Is it clear?
No, this. Yeah, 1 minute. The minus delta t is coming in a numerator or denominator or separate term.
No, it is in the numerator only. 1 second.
Yeah. Okay.
So this whole thing is in exponential. Is it clear now?
Yeah.
Yes, sir. Just a moment over here. This exponential, what you are saying is, so exponential of the sum of these two, right, sir? Gamma and delta?
Yes.
Okay, correct.
So these are all empirical formulas, and we do not have a derivation as such for all of this. So these are basically suggested based on experiments and the different experimental results. This is suggested. So as I was telling, the difference between the positive and the negative RIV pulse. So for a positive RIV, these positive ions hit the neutral molecules. And due to the higher mass of positive ions, this rise time and the tail time will be higher. Whereas for a negative RIV pulse, these are the different characteristics which has been observed based on the different experimental results. For a negative RIV, rise time is very small. And that will be followed by a gradual exponential. Okay, so these are the different characteristics of the positive and negative RIV. Next, we will be looking into some different aspects of RIV measurement. And before that, we know that, so what is the main issue with this RIV? So when this RIV signal frequency that matches with the frequency of the transmission line or the power frequency, the interference signals, that is these RIV signals will overpower this, the interference signals will overpower these RIV signals, and which can cause any kind of disturbance. Thus, it should be noted that these transmission lines should not generate RIV at all, or even if it generates RIV, that should be well within the controllable limits. So basically what I told, I'll repeat it once again. So this RIV is basically generated due to this collision between the electrons and the ions and the neutral molecules. And when this RIV signal frequency that matches with the power frequency or the frequency at which power is being supplied in the transmission lines, so that then the interfering signals will overpower the RIV signal, and that will cause disturbance in the power distribution network. And hence our transmission line should not generate any kind of RIV, or even if it generates, that should be within our controllable limits. And for that, we need a specialized circuitry, specialized network, which can measure this RIV. So next, we will be looking into the circuit for RIV measurement. So this RIV measurement circuit, I'll first draw it, and it's a bit difficult to draw in this small space. Big circuit, and try it. Just I'll draw the circuit first, then I'll be explaining that. So this is the basic circuit for measurement of RIV. This is basically the filter, and this is the high voltage source. This is my test object. This is the coupling capacitor, which is almost equal to 1500 and picofarads. High value capacitance. This is my L. This is a sphere gap for excitation. These are the different components. L0, RG. This will be a C for impedance mismatch or impedance matching. This is my cable. This is my RC, and this is my NM, that is noise meter. This will tell me what is the audible noise also. So basically, this is the circuit for measurement of this RIV. Please, everyone, you should note down this circuit. So this is the circuit which is used for measurement of radio frequency, radio interference voltages. So I'll describe each section now of the circuit. So the first is the LC filter. So this LC filter is basically to absorb any RIV signal from the test object. So the LC filter is present to absorb any RIV spurious signal from the test object, which might destroy the high voltage source. So this high voltage source can be a testing transformer. Testing transformer, or you can have a Marx generator. So this NC filter is present to absorb any kind of RIB signal from the test object, which might destroy our high voltage source. So the entire RIB, it doesn't, this RIB signal which is generated from this test object, it will not be transferred to this filter side. So there are two paths for the RIB signal, right? This is one path. This is my another path. So here this L and C are present, and that will be the impedance is arranged such that it will absorb any high frequency signal. So it is not going this side. So it has to go this side. So the entire RIB is dropped across the coupling capacitor. Across the coupling capacitor CC. And due to this, it will develop an electric field, which develops an electric. And depending on the frequency, if the frequency is high enough of the RIB signal, magnetic field is generated. Till now, is the explanation clear? And once this electric field is created by the CC, and depending on the frequency, if magnetic field is also created, then there will be a continuous transfer of energy between this CC and L. There will be a continuous transfer of energy between CC and L. Transfer of energy between CC and L. Hence, we get a pulse like this. So there will be, hence we get a pulse. So we get a pulse like this. Due to this continuous transfer of energy between this inductor and the capacitor, we'll get a pulse like this. Magnitude of this pulse will give me magnitude of RIB. And pulse duration gives frequency. And one more thing, you see this one, this cable is connected, right? So why is this cable connected? So any high voltage output, we cannot directly connect across a meter because there will be reflections. There will be traveling wave phenomena, right? Because of impedance mismatch. So the cable is connected because any meter across a high voltage equivalent. So this cable is connected because any meter or any measuring instrument meter cannot be directly connected across a high voltage equipment. Because due to reflections, there will be magnification or intensification of the voltage and current waves, and that will cause damage of the HV equipment as well as the meter also. Hence, the cable is connected by impedance matching such that there is no reflection. So is this clear, the operation of this circuit? Any confusion, any doubts, you can ask. Any doubts, any confusion? Otherwise, I have to start a new topic. So we'll be starting it in the next class. So any doubts, any clarifications, anything is needed?
Sir, repeat करेंगे क्या एक बार?
Which one you want to?
Last from RLC circuit.
Okay. So, okay, I will explain this RIV circuit once again. So as you can see here, there is a high voltage source like a testing transformer or a Marx generator. And we have the test object whose RIV we want to measure here. And there is an LC filter. So this LC filter this LC filter is designed in such a way that it will block any kind of RIV signals, because if these RIV signals are passed on, it can move to the high voltage source and that can destroy this high voltage source. So the entire RIV signal is now moving towards this. It will be moving towards here. It will be dropped across CC. Now there will be a since the RIV signal is dropped across CC, it will develop a electric field because it is getting an excitation. Obviously, capacitor will develop an electric field. Now, depending on the frequency of the RIV signal, if it is high enough, a strong magnetic field will also be created due to the presence of this inductor. So this electric and magnetic field, there will be mutual coupling between the capacitor and the inductor, and there will be continuous transfer of energy between this coupling capacitor and the inductor L. And hence we will get a pulse like there will be on time, off time, on time, off time. Like this, we will get a pulse. And from this pulse, the magnitude of this pulse, we will get the magnitude of the RIV, and from the frequency of the pulse duration will give me the frequency. And this cable is connected because any high voltage equipment cannot be directly connected across the meter. Hence, we will not get. Is my voice audible?
Yes, you are
Yes,
audible.
sir.
Audible.
It is clear, right?
Yeah.
Okay. So this cable is connected basically because we cannot directly connect any high voltage equipment to a meter, because this high voltage signals will, depending on the traveling wave phenomena, there will be intensification of these signals due to traveling wave phenomena, due to multiple reflections and refractions. There will be multiplication of this voltage signals, and that can destroy the meter. Hence, we connect any high voltage equipment to a meter through a cable, which you can see here, and with the appropriate matching impedance, so that there is no reflection from the high voltage signal, and hence our meter is safe. So this is basically the circuit or the theory behind measurement of RIV. Is it clear now, or any other questions are there?
Yeah, one question. Can you give any example for one test object?
Example of a test object.
Yeah.
It can be any kind of RIV generating this objects. Like 1 second. I'll It can be a transmission line, like an excited transmission line which is generating corona, that can give me RIV. Because due to this RIV, due to this corona discharge, which is if you see the corona discharge pulse or the partial discharge pulse, that is a very high frequency pulse. So those kind of sources, I mean, exactly what will be the test object, I have to think. But as far as my idea goes, it is the any kind of source which can generate an RIV, whose RIV we want to measure. It can be a
Yeah,
transmission
that is
line
okay.
conductor. Hmm.
Yeah,
Yes.
in that case, if you are taking a transmission line,
Hmm.
the set, how, I mean, we'll go to the site and we'll rig up the circuit, we'll to do the experiment.
It is a, yes, it is on-site experiment only. We have to de-energize the line and then we have to perform the experiment. Most probably, still I am not.
Yeah.
Yeah. I'll look into it.
Okay. Then one more thing, what is the role of sphere gap here?
Sphere gap is actually provided for the excitation. If we, 1 second, just let me think. This is a kind of switch. I think it is for surge protection or something. It is not actually a sphere gap. It is some kind of switch, which is like used for surge protection. If any kind of surges come in the line across the inductor or the capacitor, I think it is for protection. I'll note down the questions. I can get back to you. Soft sphere gap. One more question. Okay. Anything else?
Then the capacitor C is given, no, 0.1 microfarad.
Capacitor C. Yes, that is for impedance matching. This capacitor and this
Okay.
RC. That is for matching
Okay.
the impedance, so that there is no reflection from either ends.
Okay.
Anything else? Any other queries? Any other questions? Anyone? So if there are no more questions, I'll close today's class. Everyone is fine?
Yeah,
We'll
fine.
again, yeah, we'll
Yes, sir.
again meet on next Saturday.
Okay.
Thank you.
Okay, sir. Thank you.
Thank you. Thank you, everyone.